He's going to talk to us about dynamic inference and rhythm, perception, production, and synchronization.
Yeah, thank you everyone for being here. Yeah, so I've got this weird background that takes me from computational neuroscience into music. I've tried to find some ways to bring these things together, and you can be the judge of how well that's been working for me. I'd like to do some thanks in advance. I've got a wonderful undergrad researcher and a postdoc I'm working with who have collected some of the data I showed towards the end. And this co-author has been doing some of the modeling work with me. I also had some of these ideas in the EEG lab that I work with at MIT. And this is Ani Patel Tufts, who played a really big role in bringing me into the world of music cognition. Wonderful music technologies. So the big questions that I'm interested in. First one is, how do we use fragmented sensation to create continuous dynamic percepts? And some examples of this include the often cited occluded visual motion. We're able to maintain a sense of movement as we watch something pass behind an obstacle. Obviously, bats are really good at this. They send out little pulses and get these little fragments of sensation and are able to construct this dynamic understanding of what's going on. And of course, all of our vision is fragmented in a way. We're constantly making these little movements, collecting new bits of information and trying to piece them together into a big moving picture. And then the other big question that drives this work is how do perception and the prediction of dynamic processes in the world relate to self-movement, a movement of ourselves. I mean, as humans, we're really good at imitating others' actions and mirroring them. And so our ability to predict how something's going to unfold can, we find ourselves able to do it ourselves. There are various reports of actually imitating something, helping us understand how it works. So our ability to perform an action can help us understand what that action is. There's this wonderful example of completing other people's sentences. Some people find themselves compelled to, if somebody's slowing down to finish the last word in their sentence, it can be a really powerful driver to speak, just because we have a very strong prediction of what's coming next. So there are these interesting interactions between self-movement and prediction itself. And the Drosophila, the little example which contains the world, for me, is the perceptual and motor entrainment to rhythms. So I find I can address a lot of these questions from within that. So what is entrainment and a beat? Well, a rhythmic stimulus often gives rise to a sense of some kind of periodic pulse or beat. And start moving along. Even though not every beat has not every beat has an event attached to it. So we experience right there, we experience a beat that doesn't have a sound. We hear sounds that aren't associated with the beat, but somehow we understand what's going on. And we're able to predict when things will happen next. So this involves some kind of maintenance of a phase of this cycle of a beat, and also maintenance of some kind of tempo that we've gathered. So we know how fast things are going to continue to go, and we know where we are in the cycle of that underlying beat. And that understanding of where we are in that cycle and that tempo provides structure for anticipating the events that are going to come up, and structure for planning actions, which is motor entrainment. We can move along with it. In fMRI, people have looked at people listening to beat-based rhythms. And the supplementary motor area almost always shows up on these experiments. It's right here, supplementary motor area in free SMA. I'm going to highlight that in a sec. It's been shown recently to be causally important to beat perception. If you modulate it with electrical stimulation, with transcranial direct current stimulation, you can improve or worsen people's ability to discriminate between beat-based rhythms. In all these studies over here, it's shown to light up in fMRI when people are doing beat-based listening. And the SMA is implicated in a range of different functions, including the enhancement and suppression of self-generated sounds. That'll become more relevant a little bit later, but there's various papers showing that. So what's going on in SMA? Well, people have looked at this in monkeys, and when monkeys are turning a crank, doing some kind of cyclic action, they visualize firing rates in a lot of different units in the brain in the SMA of these monkeys. And if you do a dimensionality reduction on all those units, you see the firing rates tracing out loops in this high dimensional space for every crank turn. In this particular case, the monkey turns the crank and scrolls the little scenery by, and we also see these loops evolving linearly in another space or in another dimension. And so what we end up with is some kind of abstract, what seems to be a representation of the state of the monkey's action, where it is in the cycle. And in a related task, a monkey is tapping along with a metronome, a visual or auditory metronome. It gets a couple of stimuli, and then it needs to continue to tap along. And they successfully get monkeys to do this. And you see the similar loops in the SMA firing rate space. But especially excitingly, even when the monkey is just waiting for the next move, you still see these loops of activity continuing to play out. And so what you're seeing is non-movement time intervals that are also being represented by these loops. And so we've got some kind of abstract representation of the state of the cyclic action. It's not just reflecting what the monkey is doing motorically, it's also showing us where we are in that cycle. Pulling a little bit more data from this experiment, during this, while monkeys are synchronizing with those cues, you start with a bunch of cells in the supplementary motor area that are time locked to the cues it's listening to. So no matter whether the monkey taps early or late, you see those cells going around the same time in the cycle of the thing it's listening to. And then progressively, as it continues to tap along, you see more and more of those cells that become aligned to the movement, and fewer of those cells aligned to the sensory cycle. One idea is maybe there are two representations happening in the same place. We've got some kind of representation of the sensory cycle the monkey's listening to, the metronome, and some kind of representation of its own movement. But what I would propose is that the supplementary motor area is drawing on sensory event timing in some kind of representation of action. In other words, it's got one representation that's drawing on both these sources of information. Let me just spell that out a little bit. What I'm proposing is that the supplementary motor area firing rates are using sensory input in the form of the metronome and perhaps feedback from the monkey's actions, and intrinsic dynamics, which can allow these firing rates to keep unfolding even when the monkey's not moving, to keep track of the state of some salient, predictable process in the world, which could be the monkey's movement as he's turning a crank and maybe not listening to a metronome, or an external process, he's just listening to a rhythm, or some combination of those. So if the monkey is synchronizing with the rhythm, then what may be represented in the supplementary motor area is some conflation of this predictable process of the monkey moving along the Sept. And so we're drawing on all of these sources of information and creating an intermingled representation of this self-other integrated predictable process. With most of the rest of this talk, I want to just explore that idea and see what the implications of that are and how we can model it and how we can understand what's going on. So first of all, how do we keep track of things that are moving in the world based on observations and based on predictions? So there's a simple Bayesian solution to the problem of tracking something moving in the world. It's Kalman filtered. Something like that is what's happening when you see your little icon on the map in Google Maps. And what it does is it takes estimates of where the car was a moment ago. It predicts where the car will be in a moment based on the dynamics of the car and how fast it can be moving. It takes a measurement from GPS, and then it integrates those things with each other. Using this as the prior, this is the likelihood, combines those into an optimal estimate of the state of the car. It's a great way to keep track of how something's moving if you think you have some information about how it's moving. Now, this has been hypothesized as a model of both the brain keeping track of a moving stimulus and also the brain keeping track of its the movement of its own body. There are various papers, including a pretty recent one, showing that a lot of different things can be explained in terms of the brain carrying some kind of Kalman filter of things it's paying attention to and of the state of the body. This thing I'm going to present next is some modeling work in which I posit that maybe our keeping track of the beat underlying a rhythm takes place according to the logic of Kalman filtering. So the idea is that we estimate and represent the instantaneous evolving phase of the cycle of the beat, how close we are to the next beat, how far we are from the one before it, using sound events, these rhythmic events, as single observations, and predicting the advance of the beat in between based on tempo. Now, there's a whole question of how we figure out the tempo, and actually this model can be extended to not only infer the phase, but also infer the tempo. I won't go into that in a lot of detail. But we also have this uncertainty. So those estimates in the Kalman filter are estimates made with a certain level of precision. We have the prediction with a certain amount of precision, and we integrate the likelihood, which we have with a certain amount of precision, and we maintain that state with a certain level of precision. But because those measurements are noisy, and the car's movement is noisy in respect, we end up with uncertainty. And in this case, we have uncertainty due to the inherent noisiness of timekeeping and the inherent noisiness of auditory processing times. And so this is going to look a lot like Kalman filtering. We predict that the underlying beat cycle phase will progress steadily in time. So there's dp equals dt, or dt equals 1, plus some Brownian noise. So there's some noise in our own timekeeping processes that make it seem like the beat's not unfolding perfectly steadily. Our sense of time can stutter, our brain dynamics are noisy. So the brain maintains some kind of distribution over the phase of the cycle, including uncertainty. I'll mention a couple of bits of experimental evidence suggesting that we actually do maintain a sense of uncertainty. One clear example is that we lose the sense of the beat once the stimulus goes off. So there's clearly a sense in which we become uncertain about the phase of an ongoing cycle when we lose information. The simplest option for the brain maintaining a distribution over a cycle phase would be to assume that it's Gaussian. And in that case, we've got a mean which is progressing steadily around the circle. And then we've got a variance, which is our uncertainty about where that cycle is in its process. And this variational approximation, assuming a Gaussian distribution, is what's used by Kalman filtering, and a lot of variations on predictive processing models, which are these models of how the brain acts like a Bayesian inference engine. And how do we interpret sound events when we hear them? Well, we have some kind of expectations that are a function of the beat phase. So we expect events with a high degree of probability on the beat. For those of you keeping track, this is a point process rate function. So we expect events to occur with a high probability right around the beat with a certain degree of precision. And then if we're listening to something that's subdivided, something that has events halfway in between beats, we expect events to take place near that halfway point. Maybe this has quadruplet subdivisions, and we're listening to something where we expect events at these fractional positions in the beat. So this is just an expression that the probability of an event occurring is proportionate to this rate function, which is the sum of a bunch of Gaussians. So this is just again the sort of the simplest model I could lay down for how our expectations for events depend on this underlying cycle. And a fun analogy that a colleague Annie Fell helped me come up with was that it's like we're listening for a runner who's running around a track in the dark. And we can't see exactly where he is, but he occasionally trips over these bells we left on the track. And whenever we hear a sound, we know he's right around there. We know the cycle of the beat is anchored at that point. That there's where we started. And then as he continues to run, we become less and less certain until we're starting to lose track of where he is until he hits these things here. And so we're doing this inference on the position of a cyclical process. And when we solve this, we get a set of ODEs for the estimate mean mu on the circle and variance or uncertainty as a function of so those change in time. Equations are available on request afterwards. I don't have lots of anyone's pages with symbols. But there are also these discrete resets. At every sound event, we update that mean and variance. So this is sort of the simplest picture I could put together of doing this process of dynamic inference of a hidden state that's moving cyclically based on these discrete sound events. If we look at how this plays out over time, we can see our estimate of cycle phase. This is the circle on the x-axis here, and we can see it spreading out as we become less certain. And then when we hear a sound, we update that and get a much clearer picture of where the cycle is at that moment in time. And here we can see it on time is the x-axis, phase on the y-axis. We can see phase progressing forward in time, and then at the sound we become much more certain about the cycle phase, and we become pretty certain that it's actually very close to phase zero because it's for the second. Yes, so this is the event arriving later than expected. And you can apply this model to make sense of a lot of complex rhythms. So here we're listening to the one I played at the beginning. And you can see this playing out over time with uncertainty decreasing at every event and increasing in between events. And if you perturb this whole thing in time, if you introduce some little bit of a temporal perturbation, you can see it getting corrected progressively, especially when events occur that align with strong expectations, in other words, on the beat. And so this model actually will allow you to parse rhythms in a very similar way to the way that a human listener would parse them. It also has a fun relationship to the mechanistic models that have been made of similar processes. So people have posited that maybe we extract rhythm or extract underlying cycles from rhythm using systems of oscillators. And this model can be visualized as an oscillator. So if you visualize this uncertainty as a small radius and low uncertainty as a larger radius, then this is actually just a big force oscillator. So it's a very specific force oscillator, but it's one that advances in time, and then each sound event gets mapped onto a different phase and radius. And we can see that play out. And so what we have here is this mapping from an inference process onto this mechanistic underpinning. So this tells you what kinds of dynamics are necessary to actually implement this computation. This can be fit to data. I went through the process. I won't give all the details here, but this is an experiment done in 2007 where people tap where they think the next beat is going to occur, and the various subdivisions of the beat or the beat themselves are perturbed in time. And you see how much people correct their tap based on those perturbations. And they looked at that over 2 different tempos. And just by adjusting this template of expectations appropriately, we can get really similar behavior to the experiment itself. We can see a pretty close correspondence to each of these files. I'm happy to come back to this. So as a model of rhythm perception, before going back to the brain, this develops the idea of entrainment to a rhythm as an example of a more general process of dynamic inference. It links it up with this implementation of an oscillator. It also accounts for specific aspects of rhythm perception as natural consequences of uncertainty tracking inference. So one of those, which I visualize here, is that one thing that falls out of the equations is that if you have very strong expectations for something that then doesn't happen, it actually distorts your sense of the passage of time or of the advance of the phase of the oscillator. You think something should be happening right now, it's not happening, therefore the phase of this underlying cycle must not be as advanced as I thought it was. And so you can create illusions that are very similar to those seen in humans when we listen to a cycle is subdivided and then those subdivisions are omitted. So this reproduces some interesting psychophysics effects like that. Also has some interesting implications for what happens when we misinterpret a rhythm that has syncopated events in it. I have 2 slides on this as well. And this model can extend to describe the process of inferring tempo. in the process of inferring the structure of events over the course of the beat cycle, or meter, and the effects of enculturated expectations. So people from different cultures here meet in different places. But the direction I want to go with this most directly is back to this picture of supplementary motor area. So if you recall, my proposal was that the supplementary motor area firing rates are using sensory input and intrinsic dynamics to keep track of the state of a predictable process that may be the organism's own movements, or external processes, or a combination. And here I've been talking about the process of doing this kind of inference on an external process, a rhythm we're listening to. But you might imagine that the process of keeping track of your own cyclic movements might be very similar. We get discrete feedback, for instance, from each of our steps. So if I'm walking, I hear the rhythm of my feet, and that information may be very useful in actually keeping track of my own walking and understanding where I am in my stride. Or then there's the combination of the two, where we're synchronizing with music. So the question is, how do we incorporate self-movement into this kind of model? Well, the same Kalman filter can be applied to monitor the phase of self-movement based on our own feedback and our prediction of the dynamics of our body. Or to integrate external and feedback cues into a single estimated phase. So here, we may be listening to the sensory feedback, both tactile and auditory from our own tapping or walking, and weighing that with a certain degree of precision in order to inform an estimate of the phase of our own actions. And we also may be doing weighted integration of two sets of cues, for instance, a metronome and a tapper, into this one picture of the phase of a predictable cycle, which is bringing in both my own movement and the thing I'm listening to.
Excuse me.
Yeah, go ahead.
So if it's tapping a finger or something, like that suggests that there's already some cyclical process going on in the brain. Is that assumed to be a completely separate process from this entrainment?
Well, so when we're walking or something, there are central pattern generators that play a big role. So I don't need to totally generate that cycle entirely on my own. Right. But we're also able to update those things and adjust our stride as we go and adjust the progress of tapping based on feedback and based on sort of this real-time back and forth. And I think that the way in which we are monitoring and adjusting that is related to this process. I can maybe speak more to that at the end also. But yeah, I think that in addition to just having motor pattern generators, this process of tracking our own actions is also closely related to controlling them. So this is effectively a Bayesian two combination framework, where we're using two different sources of information, weighing them both by a certain amount of precision, and using them to estimate a hidden process. This kind of two combination accounts for some interesting results. In Manning and Schuck's, this is from McMaster University in 2013, they had the participant listening to a tone that would be beep, 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 and then they'd have the participant either tap or drum or not tap along. And when the participant tapped along themselves in here, they were much more accurate in judging whether a final probe tone was early, late, or on time. And musicians can also they have the experience of tapping along with something in order to make perceptual judgments. And so this then would largely account for that effect of self-action in our timing precision. Because what we're doing is we're listening to our own bodies and using those to partially reset and adjust the reading on our clock, which is inferring the state of this program cycle. So if we incorporate this into the model, we're effectively just treating motor feedback as another rhythmic input. Our internal clock is partially entrained by our own motor feedback. And so here you can see this little reset where when I hear the metronome click, it makes me think, oh, we're close to phase 0 now, if that was the beat. But when I hear my own tap, my estimate also adjusts. And so my new phase estimate is a weighted average of my prior, where I thought the phase was before anything happened, the metronome click, which is like listening to, the external signal, which I'll suggestively call the other, and the self. And so we're doing this weighted average in order to incorporate all these three sources of information. And the precision of these two different expectations for my own action and my expectations for the click might be affected by my own attention to those different streams, or the sound quality themselves. So to try to round out the picture, so we've got, at this point, we're now perceptually entraining. We're following the rhythm that's created by an external cycle and our own movement. And when we motorically entrain something, when we tap along with it, what we're doing is we're using that perceptual inference to as a normative guide for our own movement. So we just complete this little loop here, and we say, now the supplementary motor area clock is acting as a guide for the timing of my tap. And as I put these, right, as a side note, this is all I'll say right now about active inference. But there's this idea that builds on the ideas of the Bayesian brain that says that our actual self-motion is guided by inferences about our self-motion. In other words, the belief that my hand is going to go up or that I'm going to tap at a certain time is the one and the same as the process that guides me to do that. So it's like, instead of getting motor commands, I have strong priors about what I'm going to do. And so this doesn't necessarily require active inference to be a consistent sensical model, but this is consistent with that idea, because we've got this situation where we're doing inference about something that is incorporating information from our movement, but then we're using that to guide our own movement. This actually accounts for some other interesting experimental results. Way back in 2002, people doing psychophysics of entrained tapping showed that if you're tapping along with something and there's a little perturbation in the metronome time, we'll make an adjustment in either direction, early or late. But if we skip a tap at that moment when that perturbation happens, we make a much larger adjustment. Similarly, if we start tapping after that perturbation, we make a much larger adjustment. And that makes it sort of hard to reconcile results from perceptual entrainment and actual motor entrainment, because we have to account for this. But in this model that integrates in self-motion and the external cue, this is naturally, this falls right out because of the dynamics of uncertainty. Because these self-generated stimuli from tapping effectively are competing to again, with their own respective degrees of precision, in order to dominate our internal estimate of phase. And so when we're doing a continuous tap, then we end up entraining partially to our own generated feedback and just continuing to tap steadily. Whereas when we start right after the perturbation, we don't have that additional input, and we make the adjustment based on our inferences about the external side. So this is all consistent with this test case for this model. A second test case for the model that I was very excited about as this model came together was that if motor feedback is being treated like its own metronome, that's weighing in on our estimate of the perceptual phase of something, then if we delay that motor feedback in some way, that should actually delay the subsequent tap. And so I've done this experiment now with a small cohort of pilot participants, in which people are tapping along with a metronome, and every time they tap, it makes a sound. And then we transiently delay one of those sounds. And sure enough, at least for our first 5 pilot participants, we see that they are entraining to the sound that they're making themselves. In other words, when that sound is delayed, their next tap is also delayed. Supporting this idea that self-generated stimuli and this externally generated cycle are being conflated with each other and similarly used to inform the same dynamic estimate of an underlying cycle. We just collected some non-musicians about a week ago, and we see similar things, but noise theory is good. So these all come together into what I'm calling an integrated picture of rhythm and motion tracking as well, I guess I call it active inference and supplementary motor area, where these observations in monkeys showing firing rates, tracking out these loops in this high-dimensional space is now abstractly represented as an inference process in which the monkeys are inferring the state of their own movement based on feedback, based on their own taps, and based on the metronome that they're listening to. So where can this picture shed new light? So this is all a fun exercise, but what can we actually learn from this? There are two conditions, well, there are more than two, but there are two specific conditions in which sensory motor entrainment to rhythms is impaired. One of them is in autism. It's been shown that people with autism on average will show less error correction. They'll less of an adjustment to synchronize their tapping with each individual metronome. Now that suggests that maybe the metronome is just not having as much of an effect in the brain in terms of aligning that perceptual cycle. But when we have the insight that self-entrainment, that the person's own tap is always competing to dominate that estimate of underlying phase, you realize that the same weaker error correction could be caused by stronger self-entrainment by motor feedback. More precise motor feedback means that you're going to make smaller adjustments to errors relative to the metronome, which is consistent with an EEG study in which reduced audio motor, in which EEG responses to self-generated sounds were attenuated in neurotypical participants and less attenuated in autism. In other words, the brain made a larger response to self-generated sounds. So that would be consistent with this weaker entrainment or less error correction being related to the precision of self-generated sounds. And this could be related to the fact that the observation of repetitive movements in autism, which may be weighted more heavily in terms of in training your own internal clock. So I'm actually going to be recruiting a cohort of autistic participants this year, and we'll be trying to pilot some tasks in which we look at the precision of motor feedback and entrainment. Another condition in which rhythmic entrainment is affected is stuttering. So stuttering is associated with impaired rhythm perception and synchronization, and seems to involve altered processing of auditory feedback from speech. So the question is, could both of these be understood as a single difference in entrainment? If their auditory feedback from their own speech is being processed in a different way, and that process is one and the same as our integration of external rhythmic sounds in order to form a dynamic underlying percept. Maybe both of these things are parts of the same elephant and could be explained in the same language as one underlying difference between the stutterer and the neurotypical participant. So that takes us to the end of this presentation. I'm curious to hear your thoughts. Thank you so much for bearing with me.
Questions? Yeah, just a quick warning question. So when you're having people do tapping and then you remove the auditory fluid, they can still feel themselves tapping something?
Yes. So
it's a little bit of self.
I'm doing an experiment with haptic feedback as well. I got a haptic device where we'll actually be able to delay the arrival at the next point. So we can control all of the feedback for movement because we're perturbing the movement itself.
So you know, if you see that effects, but it's not quite as large as you would have expected, given that it's for that.
So it's definitely, we do a 40 millisecond delay to the auditory input, and what we see is closer to a 20 millisecond delay in the movement. And so there's a lot of headroom, and I think if you actually delay the entire movement and give tactile feedback at the end of that will be a more powerful effect. Yeah. We also did it the same thing. I didn't show this data, but the same thing for continuation tapping, where we discontinued the metronome and now they're just tapping, and you delay the feedback, and you see an even clearer result there, where at that point they're only inferring the phase of their own tap, but when you delay the feedback from that, it also delays the subsequent tap.
was just wondering if you can control for the noise by just. Mind wandering, so on, so
Yeah, and so there would be a lot of feedback you'd have to get during that process. I guess after every trial, you'd say, how was your attention at that time?
Yeah, or like every like 9.
Right, I guess that would be better than nothing. Yeah,
Yeah.
I mean, best of course would be to stick a bunch of electrodes on them and
Yes.
just not impossible.
Going back to the feedback place, so when you say like feedback on tapping, what kind of feedback? Like if you remove the sensation of touching and tapping, but there's still the internal proprioceptive feedback. Are you remove that? Never change that in any way?
So, I mean, in the haptic version of this experiment, we'll get to control everything, because
What do you mean? Like how are you gonna do it?
what's that? So I mean, I guess maybe a more direct answer to your question and to yours as well is that if I wanted to spell out this model in excruciating detail, I could assign a level of precision to the auditory self-feedback, to the tactile self-feedback, to the proprioceptive self-feedback, and say the whole thing is a weighted combination of all of these different things. And so we'll expect to see a little bit of a shift induced by delayed auditory feedback and a larger shift induced by just delaying everything. But yeah.
Sir, to the beginning of your talk, you mentioned to be able to model this in a most simplistic way. You assume that the chances of something happens in a small interval is proportional to the rate. Is that the only assumption you're making, or you're making assumptions about like independent increments?
Yeah.
Do you
So
make those assumptions? So
you-
are you following the Poisson?
yeah. So I'm making it an inhomogeneous Poisson process.
So it's inhomogeneous.
Yeah. I mean, modulated by the underlying sector, so that's the rate goes up and down. You can add history dependence, and once you do that, you can start to at least have a descriptive model for all kinds of ways in which the actual heard rhythm starts to change your expectations. And so, I mean, there's a long ways you could drive down this sort of descriptive modeling path in which, yeah, I mean, my expectations for when certain notes will happen can be modulated by what I've heard with these other notes. And you can also get really close to these probabilistic models of music perception, but those don't do a good job with timing. And so by bringing in things like this Poisson process that's modulated by rate, we bring that description of timing into this as well. Yeah.
Are there time cells in the supplementary motor area?
Right, time cells. So yes.
How would that fit into this?
So the group that did this work here, their earlier story in 2014, 2015 was about cells that whose firing rates would be modulated at particular moments during the cycle of the monkey's movement. And you would see cells that were anticipating the movement. You'd see cells that were immediately turned on by the click. You'd see cells that would ramp in between. And this whole zoo of cells became a very complicated story. And so then they just put this in a high dimensional space, did PCA on it, and we're like, wait a sec, maybe there's a bigger picture we can get here, in which rather than looking for the activities of individual cells, we look at these whole things in a high dimensional space. And that's how they ended up with these looping pictures. But the earlier story is that I mean, the way you get around the circle is some cells ramp up their firing, some cells ramp down their firing, and then the cyclical process happens. Those cells trading off from each other. And I think if you make a bunch of time cells go in a cycle, and then you plot that in a high dimensional space and do a PCA reduction, you end up with something like this.
But if you do that, you need all the Bayesian mechanisms.
So, I mean, you're answering different questions. I think that there's the question of the mechanistic underpinnings of this. And that's a whole direction that I could have gone, and I'm to a certain extent also planning on going moving forward, is looking at how networks can generate this kind of activity. What the Bayesian perspective, I think, gives us is, I mean, it brings us together with ideas about the control of body movement, and also brings it together with these bigger ideas about prediction error and prediction error minimization and the Bayesian brain and predictive processing, and it's trying to construct a bigger picture of the cognition involved in this. But yes, the question of which cells are speaking to which other cells, how a network has to be structured in order to create this entrained activity. I think that's a really interesting direction as well. And so in another thread, I'm training networks to do something like this, and seeing what we get. Thank you, everyone. Last question, Jeff?
So, seems like the crux of what you're doing here is basically a Bayesian combination of information.
Bayesian Q combination, yeah, combination.
And so you showed that really nice multicolored graph that matched so closely to the data.
This one? Or,
Okay, yeah, that too.
or
I
is
think
it the different
what
one you're thinking?
it had, but it doesn't really matter.
Okay,
So to get those fits, or
this,
just has to go back about 4 sets. There.
oh, this one, yeah.
Like, is that
This is just a matter of adjusting the 3 precisions, basically the amount of uncertainty that you accumulate over a given, interval, the precision of the metronome you're listening to, and the precision of your own tap feedback.
Okay.
And by tuning those 3 parameters, you can match these graphs really nicely.
Okay.
And then that other graph I was showing, you have to tune parameters for how we treat subdivisions. So this is just a single metronome that represents like one ongoing beat. But with those other experiments, it's like, yeah, they're shifting. You're listening to and each of those little things can get shifted in its own way, and we respond to those timing shifts differently. And so at that point, you're now assigning precision to each of those different expectations for those notes, for those sounds. And so when you fit those parameters, then you can end up matching these more complicated experiments. It makes you think a little bit about how a given movement that we make will have multiple feedbacks, multiple things telling us that we're in the right place at the right time, multiple ways of knowing where I am over the course of my action. And as my action unfolds, I'm going to be weighing each of those, using it to reassure myself that I am where I think I am, or adjust to make sure that I am sequencing my action correctly. And so thinking about the subdivided beat as just expectations for different points of feedback over the course of an action-like process, a predictable process. And I think this Bayesian perspective can kind of bring those things together in a nice way.
Yeah, but could you sort of gave this enticing preview of stuttering, and maybe can you just talk a bit about that and the fact that I think I've heard that people who stutter don't necessarily stutter when they're singing.
Right. So I mean the data linking stuttering and rhythm perception is really compelling at this point. Like people who stutter have a much easier time speaking along with a metronome than they do speaking without. People who stutter, if you, they respond well to delayed or altered feedback from their own voice. People who stutter who tap along with a metronome show. It hasn't really been studied exactly how their synchronization becomes worse than other people's, but they show less precise synchronization. They have more difficulty discriminating between similar rhythms if they're complex and over a beat. And I'm trying to formalize the hypothesis for how that works. I think a loose idea about what might be happening is just a deficit in the maintenance of an internal beat without sensory scaffolding. The idea that maybe our speech is sequenced based on auditory feedback from our own speech, and also based on whatever our expectations are for that without the auditory feedback. So I can still keep talking even if my feedback is manipulated or blocked. But the stutterer might have a special difficulty sequencing speech without that auditory feedback. And that might translate into difficulty having a the sense of a beat there without constant input to scaffold that. So I'm figuring out the right way to model that in this framework. I think it may require a little tweak to the model that, but I think, yeah, we're gonna do a round of different experiments to see which aspects of that, including probably the delayed feedback experiment, to see whether that happens the same way.
No other questions? Let's thank Jonathan again. Thank you.